Hey Calculus class! Today we're going to talk about topic 48, exponential growth and decay. So we're going to start with direct proportion. And direct proportion is a relationship between quantities whose ratio remains constant. So when A changes, then B changes by the same factor. So for example, when you see y is proportional to x, that means you have y equals some constant times k, where k is what we call the proportionality constant. Population rate is proportional to the population size, which means that dp dt, so the population rate, equals proportional to, so some constant, times the population size. And can we find the solution to this differential equation? You bet we can. So, using what we did yesterday with the separation of variables, we are going to find the differential, or the solution to this differential equation. So, we are first going to separate variables. So, I'm going to have t's on one side, p's on the other side. And since k is just a constant, I'm just going to leave it with the t's. Technically, it doesn't matter. Now, before I integrate both sides, just a quick little side note that if I was to solve for k specifically, that means I would get that k would be equal to 1 over p, so 1 over the population size, times the rate of the population, is what we call the relative growth constant. So now I'm going to go ahead and integrate both sides. So on the left-hand side, antiderivative of 1 over p is the natural log of the absolute value of p plus some constant equal to kt plus some constant. I am going to subtract the constants to one side. So now I have the natural log of the absolute value of p equal to little kt plus k, or big K. And my goal is to solve for p. So I'm going to exponentiate both sides, and I can separate the right-hand side by using my exponent properties backwards. And e to the capital K, that's just some arbitrary constant. And so by the definition of absolute value, we can say that we're going to let capital A equal plus or minus e to the k. And so by doing that, we can drop the absolute value sign on p and at the same time replace e to the capital K with a. So that means that my solution to this differential equation is p equals a times e to the kt. And since this is the general solution, we can find a particular solution by using the initial condition of p of 0 equals p naught, where p naught is the initial population, where 0, of course, is at the start of time, or whenever you do your experiment, or etc. So by doing that, we can actually now find, using that initial condition, we can now go ahead and find a. Well, e to the 0, that's just going to give me 1. So that means a is going to equal my initial population. So this means that p of t is going to equal p naught times e to the kt is the particular solution. So now this leads into our exponential growth model. So the initial value problem for exponential growth is given by dp dt equals kp, where p of 0 equals p naught, so this is what we just did, has a particular solution of p of t equals p naught times e to the kt, where p naught is the initial population at t equals 0, k is the relative growth rate constant, and since it's a growth rate, that means k will be greater than 0. T, of course, equals the time that the population grows. And P of t is what the population grows to after time t. So, for example, if we have a common inhabitant of human intestines, which is the bacterium I cannot pronounce that, basically E. coli, a cell of this bacterium in a nutrient broth medium divides into 2 cells every 20 minutes. The initial population of a culture is 60 cells. So I want to find the relative growth rate. This means that I want to find the value of K. So I know by using my particular solution that I have P of T equals P naught, so my starting number of cells, which in this case is 60, equals e to the KT. We need another point. So basically, in order for me to solve for K, I need the value of population at some time value. Well, we know in this problem, it says that 20 minutes equals 1/3 of an hour. So that means that after the first 20 minutes, we have 120 cells, because it says that every 20 minutes, the cells divide into 2. So after the first 20 minutes, or the first third of an hour, we have 120 cells. So, and then of course, after the next 20 minutes, we have 240 cells. And then that means at an hour, we have 480 cells. So I'm going to choose to use the point 1 and 480, just because it would be easier to evaluate. I could technically use any one of those if I wanted to. So now I'm going to go ahead and solve for K. So divide both sides by 60. So that means e to the K equals 8. So that means K is going to equal the natural log of 8. So now I'm going to find an expression for the number of cells after T hours. So I just found what K was. I already know what my initial population was. So that means an expression for the number of cells after T hours is going to be P of T equals 60 times e to the natural log of 8 times T. Technically, you can leave this like that. The equation like this. However, we typically do not like to have e and natural log together. They actually cancel each other out. So that means the 8 can come on down. And so my proper equation would be P of T equals 60 times 8 to the T. All right, now for part C, we're going to find the number of cells after 8 hours. So that means I'm going to use my expression from part B, plug in 8 for T, evaluate. So I get 1,600,632,960 cells. All right, part D, we're going to find the rate of growth after 8 hours. So that means that I want dP dt, where it equals K times P. Well, I know that K is the natural log of 8, and I now have the value of P at 8 hours, which is this very large number. Multiply those together. So my rate of growth after 8 hours is 2,093,234,394 cells per hour. And part E, so when will the population reach 20,000 cells? So that means I need to find T when P equals 20,000. So I'm going to set 20,000 equal to my equation. Solve for T, so divide by 60. And in order to get T down, that means I have to take log of the base, so in this case log base 8 of 1,000 over 3 equals T. And then to get that actual number, I would plug this in my calculator to get T equals 2.7936 hours. All right, now let's talk about exponential decay. So the initial value problem for exponential decay is given by dP dt equals negative K times P, where we have P of 0 equals P naught. So really the only difference with this is that now your relative growth rate constant, K, is negative. That's what makes it decay. So it has a particular solution where we have P of t equals P naught of e to the negative kt, where P naught is the initial population at time t equals 0, K equals the relative decay rate constant, so in this case K is negative, and of course T equals time, and P of t is the population left after time t. So now let's look at an example of bismuth 210 has a half-life of 5 days. So for part A, we want to suppose that a sample originally has a mass of 800 milligrams. We want to find a formula for the mass remaining after t days. So to do that, I'm going to set up my exponential decay model, and in this case I'm going to use m instead of p because I'm looking for mass remaining rather than population. So now I have my initial starting a mass, which is 800 times e to the kt. And just like in the previous example, I need to first find the value of k. So in order to do that, I need a time value and a specific amount of mass. Well, it says here that the half-life is 5 days. So that means after 5 days, my mass is half of my initial mass. So in this case, after 5 days, I'm going to have a half of 800, which is 400. So that means I can plug in 5 for time and 400 for mass. Solve for k, so divide by 800. Natural log both sides. And using log properties, I can take the natural log of 1 minus the natural log of 2. Well, the natural log of 1 is 0. So now I have that 5k equals negative natural log of 2. So that means k equals negative 1/5 times the natural log of 2. So that means that my mass formula is given by 800 times e to the negative 1/5 natural log of 2 times t. And the e and the natural log cancel. So that means the argument of the log comes down. So 2, the negative 1/5 stays up in the exponent with t. So this gives me my exponential decay model. So now for part B, using our exponential decay model, we want to find the mass remaining after 30 days. So I'm going to plug 30 in for t and evaluate to get 12.5 milligrams. Now we want to find when is the mass reduced to 1 milligram. So that means I want to find t when the mass is 1. I'm going to solve for t, so divide by 800. Log both sides with base 2. Multiply both sides by negative 5. And it's okay if you want to leave your t as the following, but usually you kind of want to know what actual number this represents. So by using your calculator, it would take approximately 48.2193 days. All right, now this leads into Newton's law of cooling. So Newton's law of cooling states that the rate of cooling of an object is proportional to the difference between the object and its surroundings. So we're going to let capital T of little t, time, be the temperature of an object at time t, and T sub S be the temperature of the surroundings, the environment. And we're going to note that T sub S will be assumed to be a constant. Mathematically, Newton's law of cooling can be expressed as the following differential equation. So d of t dt is equal to k times t minus the temperature of the surroundings. So we're going to let y equal t minus t sub s. Then we're going to take the derivative with respect to time. So we now have dy dt, which is equal to dt dt. And if you substitute in, we get dy dt equals ky, which is the exponential growth model. And this means that the solution to the differential equation is y of t equals y naught e to the kt. So we now need to write the solution in terms of t. So recall that we have the following. Y of t will equal t of t minus t sub s. where y naught equals y sub 0, which will equal t of 0 minus t sub s, which would be our t naught minus t sub s. So therefore, we can rewrite this as t of t minus t sub s equal to t naught minus t sub s times e to the kt. So now solving for t of t gives us the solution to the Newton's law of cooling, which is the following. So the rate that the temperature T of an object that is cooling is given by the initial value problem of dt dt equals k times t minus t sub s of t of 0 equals t naught. So the particular solution of this initial value problem describing the object's temperature after a particular time t is given by t of t equals t sub s plus t naught minus t sub s times e to the kt, where t sub s is your temperature of the surrounding environment, and that's a constant. T naught is your initial temperature of the object at time t equals 0. K is your proportionality constant, and T of t is the temperature of the object after time t. All right, so let's do an example. Suppose you cool a pot of soup in a 75-degree Fahrenheit room. Right when you take the soup off the stove, you measure its temperature to be 220 degrees Fahrenheit. Suppose after 20 minutes, the soup has cooled to 170 degrees Fahrenheit. What will be the temperature of the soup in 30 minutes? So we already know what T sub S is, so the temperature of the surrounding, which is the room, and that's a constant of 75 degrees. We have our initial temperature, which is 220, and we are given that at T of 20 minutes, our temperature is 170. So using my formula from the previous slide, that means I can set up my model with the surrounding temperature, 75, plus my initial temperature, 220, minus my surrounding temperature, 75, times e to the kt. And I can simplify that. So I get that T of t is equal to 75 plus 145 e to the kt. And in order for me to find k, in order for me to evaluate this function at time t of 30 minutes, I'm going to plug in that in 20 minutes, I have a temperature of 170. So now basically I'm going to solve for k. So I subtracted 75 first. Now I'm going to divide by 145 and simplify. I'm going to natural log both sides, divide by 20. So I get k to be the following. And if I wanted the decimal, it would give me negative 0.0211. And it makes sense that this should be negative because the temperature is cooling. So it's similar to your decay model. So now I have that T of t is equal to 75 plus 145 e to the negative 0.0211 t. And in order to be as accurate as possible, you need to store this value in your calculator. Do not just round it in your calculator. All right, so now to answer my question, what's the temperature after 30 minutes? I'm going to put 30 minutes in for T and evaluate. So the temperature will be 151.8956 degrees Fahrenheit. All right, suppose you can eat the soup when it's 130 degrees Fahrenheit. How long will it take for it to cool to this temperature? So that means I want to solve for little t when the temperature of the soup is 130. So I set my model equal to 130. And I'm going to solve for little t. So subtract 75, divide by 145 and simplify. Natural log both sides, divide by that constant, and evaluate. So t equals 45.8501 minutes. Well, I hope you enjoyed learning about exponential growth decay and Newton's law of cooling. And I think you should, a fun little experiment would be if you were baking brownies or something, you could actually do this experiment and see how long it would take you if you wanted to eat the brownies at a certain temperature or something like that. All right, I'll see you in class tomorrow. Have a good night.